We're good. Perfect. Well, thank you again for coming. My name is Jeff. I'm a product manager at AWS, and I'm happy to introduce AWS IoT FleetWise. You might have seen the announcement yesterday. I'm joined here by Brian Carlson from NXP, Global Director of Marketing at NXP, who will talk a little bit about some of the things that NXP is working on and how we work together as well. So I'm excited to be here and excited to show this new product that is less than 12 hours old. Perfect. So a little bit of the agenda today. We're going to talk about the connected vehicle market and specifically why we built this product, some of the current challenges that automakers are working on and that they're facing in today's changing world, specifically the reason why we built AWS IoT FleetWise, some of the key features and benefits of AWS IoT FleetWise. Brian's going to come up on stage and talk about the S32G vehicle processing platforms. And then lastly, I want to do a little bit of a demo of the product that we launched. Perfect. So let's look a little bit closer at the connected car market. We're seeing tremendous growth in connected vehicles. Specifically, by 2030, over 95% of vehicles are going to be connected to the internet. That's compared to less than 50% today. Autonomous vehicles create a ton of data, some up to 4 to 6 terabytes each single day. To put this into context, this is over 37,000 times the amount of data that we generate on our smartphones each day. All of this culminates in over 10 exabytes of data generated and consumed by connected cars by 2025. This is a tremendous amount of data. Big data doesn't scare us at AWS, though, and more cars are connecting to the internet before. And one of the things that we've learned about connected cars and about big data in general is the importance of the 3 Vs of big data, and specifically variety. Variety is particularly important in automotive, and the reason for that is there are numerous different types of vehicles and different models. There's different variations. You can walk down the street and see 100 different types of cars. This is a ton of different variations of different vehicles. This creates a big challenge when you start connecting all of them. So let's pretend that we're an automaker real quick. Each individual car has on average 30,000 parts. This is multiplied by, let's say, 1,400 tier 1 suppliers on average. Not to mention the tier 2 and tier 3 suppliers that also go into building vehicles. This is also multiplied again by 14 average models per manufacturer in the US. This is not counting trims, this is not counting options. You can see pretty quickly that the variations start exploding. And I end up with numerous different possibilities and numerous different outcomes. So this also equals a big opportunity for data to become out of sync, unorganized, and fragmented. But what does this actually look like? So to do that, to understand what it actually looks like, let's look at an individual vehicle. The first challenge automakers and suppliers in the automotive must overcome is that a significant amount of the data on the car itself is not actually human readable. It's encoded. It's encoded in proprietary signals on the different networks on the vehicle. This could be such as CAN, Ethernet, et cetera. Let's take CAN, for example. There's multiple different networks on the vehicle itself. You've got powertrain, you've got body, you've got chassis, just as a couple of examples. There's numerous on a vehicle. These are all sending data in different formats. Could be over CAN, could be over LAN, et cetera. This is getting worse when you add in things like ADAS and cameras, radar, and LiDAR. These sensors are inputting data or sending data over the vehicle in yet another format, such as Ethernet. All of these things automakers must overcome first. This gets worse when you zoom out and start to look at the fleet in general. This is especially true for fleets of different types of vehicles. If I look at like a rental car company, for instance, that has multiple different brands, multiple different types of vehicles. But even within an OEM, we see different variations and different models. One OEM could have a diesel, could have a hybrid, could have EV, could have multiple trucks, cars. All of those different variations add up to different combinations and different unique combinations of data. So what does this actually look like in a database? Let's take a look. So we can have a single vehicle with multiple entries in the same timestamp, telling us the same information, but slightly different. The reason for this is one could be coming from the powertrain domain, and it's measuring vehicle speed, for instance, from the transmission. The same information could be coming from the chassis, measured by a wheel speed sensor. These are giving you the same information, but 2 different data formats that you must now, as an automaker, as an engineer at an automaker, must overcome. Across different vehicles, you can see even the same sensor potentially sending data in different formats. A great example of this would be a North America model sending brake pedal pressure in bar or PSI. A European model would send the same data in kPa or kilopascal. The data headers themselves without any context may not make any sense. So for example, the OEM or the engineer now has to understand what TGR cell means without necessarily, they weren't the ones that built it, they don't know. This is all problems that engineers and analysts must overcome when trying to solve problems, adding headwinds to the problems that they're trying to solve just to get to the data. So in summary, we see a couple of things. We see, first of all, that more vehicles are connected to the internet than ever before, and they're generating more data than ever before. Advanced sensors such as radar, LiDAR, and camera are exacerbating this problem. Collecting and organizing vehicle data at scale is a difficult problem, specifically because vehicles are inherently unique and different. All of these differences create a different data fingerprint. And at scale, this is an even bigger problem to solve, because as you scale, more and more vehicles increase your variability yet again. All this culminates in more data over the air, which is increasing the amount of money and time that automakers are spending. This results typically in slower communication and slower understanding of problems. Data timeliness is expensive. Just in automotive, just as it is in data, speed typically equals more expense. So because of that, and because these fleets are millions of vehicles long, simply you can't afford to get data right at the same time until now. This is why we built AWS IoT Fleetwise, to solve some of these challenges. AWS IoT Fleetwise helps tip the scales back in an automaker's favor by making it easy to collect, organize, and transfer vehicle data to the cloud so automakers can get insights about their fleets. Automakers can use this data transferred by AWS IoT Fleetwise to quickly detect fleet-wide quality issues, remotely diagnose individual vehicle problems in near real time, and improve autonomous driving systems for some of the examples. This helps automakers increase the safety of their vehicles, reduce vehicle service and warranty costs, and help personalize the customer experience. So what are some of the benefits of AWS IoT Fleetwise? First of all, we want you to be able to access standardized fleet-wide vehicle data. So accessing the unique data format of any vehicle, we want you to be able to structure it in the cloud and provide a centralized area and a centralized data schema for all of your downstream users and downstream systems to use. This is all happening within the cloud. With an aggregated data structure, automakers can now access some of those insights without having to go into each individual vehicle and understand that individual vehicle's context. Nearly all vehicles today use a standard in-vehicle communications protocol, such as the CAN bus, which is, however, even though it's standard, it's unique to each vehicle. And what we want to do with this service is bring up and abstract that to now I can use all of those different services. I can now use all of those different signals in a standardized format. Lastly, we want to be able to reduce costs with intelligent data filtering. So the intelligent data filtering is one of the key aspects of this service. It allows you to transfer only the high-value data to the cloud while leaving noise and things that you don't necessarily need to understand, leaving it at the vehicle. You're not now paying to transfer it over a cellular network. This is a key because this allows efficient data transfer and allows faster data transfer because we're simply transmitting less. This allows us and allows automakers to now detect and mitigate problems faster. Because we're eliminating the noise and reducing the data sent, I can now afford and pay for faster quality data. So let's take a 10,000-foot view of how AWS IoT Fleetwise works. And as you may guess, it starts in the cloud. This is where customers create and define vehicle models, or design twins as we call them. This is inclusive of attributes, sensors, and signals. The schema here we use is based on automotive standards, one of which is what we call VSS, or what is called VSS. And this is used to create common context and signal definition across the entire fleet. AWS IoT Fleetwise also does employ an edge agent, or an in-vehicle agent, which is used to collect information of interest to customers from their vehicles. This edge agent is optimized to run on automotive hardware specifically, such as NXP's S32G processing platform, and is entirely configurable to a customer-specific application. In fact, we give you the source code for this edge application. Once the vehicle is modeled in the cloud and the edge agent is deployed to the edge or to the vehicle, you now have to tell us or you configure what data you want to collect. This is done through creating campaigns, and we'll go over that in a little bit. Customers define these campaigns, which are essentially instructions for what data to collect and when. We only collect the data that you specify, and nothing more, nothing less. This is then what the edge agent uses to monitor this data, to monitor signals on the vehicle, collect data when an event of interest happens, and then send it back to the cloud. So looking a little bit closer, let's look into vehicle modeling first. So each of the components of AWS IoT FleetWise work together in a symbiotic manner. But for this purpose, vehicle modeling, the first way to start this process is within the console or the APIs. Customers first define the vehicle representation or the signals that represent their vehicle. This is what we call the model manifest. What this is a collection of attributes, sensors, and signals that represent that individual vehicle. Each model has a unique model or a unique virtual model, but all of this culminates and rolls up into a centralized repository. This is considered the signal catalog, is what we call that. All of the sensors that are shared between different models now roll up to a centralized catalog, which allows the same signal to be used over and over again with the same data format. Like I was mentioning earlier, we do use some standards in the automotive industry, such as VSS, or Vehicle Signal Specification. The reason for that is so we can model things like fuel pressure. Fuel pressure is now standardized using VSS for all automakers and suppliers participating in that standard across them. So now, not only is it shared across one OEM, but it could be shared across multiple suppliers and multiple OEMs. Once the vehicle's sensors and attributes are defined in this virtual vehicle model, you upload a standard CAN DBC file, CAN database file. This is how we actually read the data or understand the data sent over your vehicle's communication network. This is proprietary, so you upload this proprietary file in AWS IoT FleetWise, and we now know how to read and determine or decipher the data sent over the vehicle bus. If you no longer want us to read that data, simply delete that configuration, and we can no longer read those proprietary signals. We don't keep anything like that. So let's talk a little bit about the vehicle edge agent itself. This is what's running on the vehicle. So the edge agent is responsible for a couple of things. First of all, it's responsible for sitting on the vehicle network and understanding and basically listening in to all the sensors and signals sent over the various different networks on a vehicle. It's also responsible for secure communication between the vehicle and the cloud. It connects directly to AWS IoT FleetWise in the cloud through things like IoT Core, AWS IoT Core. Automakers install this application source code to support automotive hardware. This could be like the NXP S32 Jeep board. We also plan to support additional hardware in 2022. The key thing with the edge agent that we want to make sure is known is that everything is controlled by the automaker. This edge agent is completely in the hands of the automaker or the customer. They have complete control over it. They can manipulate the source code as they need to. Lastly, rule-based collection. So rule-based collection is where the real value of AWS IoT FleetWise comes from. Once a vehicle is modeled, the developer defines these data collection schemes in the cloud. This is what to collect, when to collect. These collection schemes come in two main flavors, the first of which is time-based, the second of which is event-based. Time-based data collection is simply, I want to collect these sensors or these signals every 10,000 milliseconds or every 10 seconds. The second type is event-based. Event-based is more, I want to collect this data when something of interest happens. This could be, for example, I want to collect brake pedal pressure when ABS is activated. Could be any of those. These can be simple or complex depending on the problem that you're solving. The ability to create and manage these rules and these filters in the cloud and then remotely deploy them to the vehicle is one of the key values and one of the key reasons we think this is an exciting service. This allows automakers to tailor their collection needs and their data capture needs based on the problem that they're trying to solve. If they're trying to understand trends, time-based makes sense. They can understand trends from their fleet of vehicles over a given set of time. If they've got a specific problem to solve, they can also now build a specific event, deploy that campaign to the vehicle, collect the data, and then once they've understood the problem or once they've solved the problem, they can turn that campaign off and no longer pay for collecting that data. We see a lot of possibilities for what you can do with this service. And specifically, we see a couple of use cases that we think are exciting. First of which, we think training computer vision models for autonomous vehicles makes a lot of sense for this service. Specifically, AVs care about small changes. They will always want to be learning about the differences. How does that stop sign look with a different shade of light, or the sun hits it a different way? But at the same time, collecting that kind of data is inherently noisy. You collect the same stop sign every time, maybe 10 out of those 1,000 images you can actually use to train your models. We think FleetWise can help with that. Secondly, minimizing warranty claims and reducing recalls. Because you have a better understanding of your vehicle over time, but you also have fast data, that allows you to react quicker and hopefully be able to minimize those warranty claims. You don't want your customer to be your canary. Improving EV range estimates is another exciting area that we think makes sense. EVs specifically are affected by the environment. So how does my vehicle work better in the cold? How does it work in the hot? How can I improve that range estimate over time? You need a lot of data to improve those, and that's where we think FleetWise can come in and help as well. Lastly, we know that the road is always changing, and because of this, automakers need to understand how their vehicles are working in those changing road conditions. By detecting changing road conditions, whether it be hazards such as ice, snow, or simply construction, I'm able to now tailor my vehicle and update my vehicle, either future iterations or in the near future, we anticipate OTA being a pretty big part as well. So being able to adjust that vehicle on the fly. With that, I do want to bring up Brian, who's going to talk about NXP and the vehicle platform. Brian?
I got this. Thank you, Jeff. So I represent NXP, a partner of AWS, and if you don't know who NXP is, we have decades of experience, combination going back to Motorola, Freescale, and Philips Semiconductor. So decades of experience in automotive processing, security. Your passport probably has our chip in there for security, or your bank cards. Enterprise networking. And what we basically did here is converge all of that expertise and technology from our side into a single chip that really matches well with what AWS is doing in automotive, and specifically here for FleetWise. So as I think everyone knows, this connected vehicles, there's not one company that can do it all. It really requires an ecosystem of partnerships to bring that expertise. And with NXP being the leader in automotive processing and the expertise and leadership position of AWS in cloud platforms, that combination came together really well to provide a solution that, as I said, not one company can do by themselves. So we mentioned the reference to S32G, and that's the processor, that's the focus here today to run the FleetWise capabilities. And what I wanted to give was a little bit of perspective on why we did what we did with this device. And it goes back about 5 or 6 years. We've been in discussions with leading OEMs worldwide on what were their vision for the future, what did they need to do, and the common thing that came across was, I need access to data. I remember still a conversation with an OEM about maybe 4 or 5 years ago saying, look, today I have people all over my enterprise that need access to data, whether they're data scientists, whether they're product managers, whether they're software engineers, they need access to data. And today we have to do special test vehicles with special test harnesses. It takes forever to get data. Our vision is to be able to get data from any vehicle in the fleet, any of my employees that has authorization access to the data from their laptop, and I guess today work from home, potentially even doing this from their laptop at home, to be able to have access real time to data to drive into real-time models, digital twins, to do analytics, to basically help run their enterprise and make their products better over time. So we've realized that vision. So the key was having the hardware that addresses these trends here that I'll talk about, but also having that software that makes it seamless and streamlined so that they can easily do this. And that's why I'm really excited to partner with AWS on this IoT FleetWise, because it brings that vision together that the OEMs have been asking for several years. So there's a lot of trends going on, and I think everyone's aware there's the mega trends of autonomous connected and electric vehicles. That brings a lot of complexity and requires new types of architectures. And I've heard a reference recently to, the automotive industry is going through brain surgery. It's on the table going through brain surgery. At the same time, it's having a heart transplant. And it's really a lot of complexity going on. The networking is changing. We're going from CAN to Ethernet, time-sensitive networking, where data is the lifeblood of that. Data is flowing through that vehicle. At the same time, we're moving towards software-defined vehicles, which needs a new brain, right? And it needs more cores and more processing. It needs new software technologies to do virtualization and to do lots of consolidation of ECUs as we move from domain to zonal architectures in the vehicle. And that drives a lot of requirements on the hardware, which is exactly what we've been working on for several years to be able to address to meet this vision that the OEMs had. So first of all is processing, and this is just an order of magnitude. It's actually more than that, but it's on the order of 10x from what's in cars in the last year going forward. Our processors actually, the S32G went into production in May, was in production vehicles in September. So there are vehicles on the road today that have this processor in it. But it needs a lot of processing to do new services that can be over the air updated, to provide edge processing, analytics, to be able to work with the cloud, to be able to download new applications over the life of the vehicle, which is typically, I think in the US, about 12 years is the typical age of a vehicle today. Networking, really important. Jeff talked about the explosion of data. So it's not only from sensors, it's from data that's being generated within the vehicle, synthetic sensors, things like this, that it's an explosion of data that requires new types of networking. We're seeing gigabit, 2.5 gigabit, going up to 25 gigabit over the next several years. Really, you need a way to process that data, to be able to pull the needle out of the haystack, which is totally aligned with FleetWise and how you want to only get the data that's important, process the data that's important, and get that to the cloud in a cost-effective manner. So you need new ways to do networking. Safety. Safety historically has been more of an ASIL B, which is a mid-range safety, but now we're seeing, as these vehicles are dealing with autonomous drive, the need for some ASIL D capability, and ASIL D is the highest level of functional safety. Again, we're talking about vehicles here, not a smartphone. So safety is a critical parameter, and there's this trend now to have ASIL D support and have mixed criticality. So I could have services that are just running QM, which is not the critical side, or high critical stuff like ASIL D, all running on the same platform, and having isolation and the ability to do that's really important in hardware. And then the other area is security. Security is fundamental to these systems, especially now with connected vehicles. And you need to have a high level of security that goes beyond what's historically been in I would say vehicle processors in the past, which is a hardware security module. So extending that to a hardware security engine that has full support for asymmetric cryptos, public key infrastructure, and then on top of that, providing isolation to resources and memory, and also the ability to address side channel attacks. So resistance to those types of things that people have found ways to break a lot of chips that are out there today through various types of penetration testing. So all of that's a lot of complexity on top of going through brain surgery and heart transplant at the same time. We needed a new silicon, a new type of processor, which we call vehicle network processor for the S32G, that addresses those trends, that is an order of magnitude of what's out there today. This maps really well to the AWS IoT FleetWise, because now we layered that software on top to provide that seamless experience. So how do we bring this to market? It's not just a chip, we have a complete solution, which is called, we have a reference design and what we call the Gold Box. And the Gold Box is becoming really popular in industry, I would say with tier ones and OEMs. Even though they have their own boxes or build it, this is a really important product for them to move very quickly, to be able to rapidly prototype, to be able to do their software development ahead of their device. In fact, we provide the schematics, the reference design, layout, everything. It's on nxp.com. You can get that today. This is all the basis of what's been used to do the AWS IoT FleetWise. So we have done a seamless integration with this. The S32G is central to this product. It has 18 CAN interfaces that come out, 12 Ethernet ports coming out. It provides a lot of those data paths that you need to bring data into the processor, and it has the security built in to bring that data to the cloud. It integrates real-time processing with Cortex-M cores, multiple Cortex-A cores, and what's unique about it is from an ASIL-D or functional safety point of view, we can lockstep even the Cortex-A cores, which I'm not aware of anyone doing that today with these cores. So it really culminates in an ideal platform to move quickly and to be able to start using FleetWise for your applications and doing evaluation. So I'd like to give a view of how this fits into the vehicle. So this is an example configuration where the Gold Box, the service-oriented gateway that has secure connectivity to the cloud, actually is central to the vehicle, very, very critical for this concept. And that's what's new about it. Traditionally, these are gateways. They're now service-oriented gateways. They provide horsepower, right? Processing capabilities now to put things like this Edge software from AWS to be able to intelligently process data and send only what's needed to the cloud. Because it's central, because it has so many interfaces, it actually has 20 CAN-FD interfaces. We have Ethernet switch integration in this box. We can basically be central to all the domains, whether it's body, powertrain, ADAS, autonomous, infotainment. All of that is centralized. We've also pre-integrated Greengrass version 2. We have the FleetWise available. All of that gives you an end-to-end solution now for vehicle to cloud in a secure manner. So together, we provide an end-to-end solution. And then finally, I wanted to talk about, we have the chip, we have the reference design, we have that box. You can work today. But it goes way beyond just the gateway because there's the rest of the vehicle. So to do that, we focused, we show a couple examples, whether it's the ADAS, autonomous, high-performance compute. The blue box we offer has 16 Cortex-A72 cores, support for multiple PCI Express lanes, heavy-duty machine learning inferencing right in the box. And by the way, a lot of people don't know this, that blue box also includes an S32G now. So it also is, I would say, used a lot in safety applications. So you could effectively combine the blue box and green box into that blue box and be able to do a lot of this directly in an ADAS autonomous system and leveraging the software. We also have the green box. In fact, that was the first project we worked with AWS on last year. We do a connected EV management system. So we're already doing things with Greengrass and now extending that with FleetWise to be able to support data to the cloud and really making efficient use of energy management, battery management, and having all of that within a powertrain domain controller for EVs. And we're able to show increase of efficiency of 20, 25, 30% of EV range by using new algorithms, having that full life cycle with model-based design, be able to do machine learning with SageMaker, and to bring that all back into the green box to improve the range of the vehicle. So there's a lot of things going on here. We're looking at this holistically as an automotive vendor because we have processors that go across the automobile, and that's what's really attractive here from a FleetWise perspective because now we can start leveraging a lot of our really new technologies that are coming, integrate that in so our customers, the OEMs and tier ones, can really easily get access to that data just from their laptop at home. So again, this drives a lot of applications. We support both the Greengrass path with IoT Core as well as FleetWise, so you have a lot of capabilities at your fingertips, all within the vehicle and support with multiple boxes or ECUs across the vehicle to gather data. One example I'll also mention, inside that gold box is the Ethernet switch, and that actually is running FreeRTOS with the IoT extensions. So we actually, from the cloud, and I think with also FleetWise, we can actually monitor all the network traffic going on in the vehicle directly from the cloud through inside that box. So it's more than just the S32G, it's also the SJA1110 Ethernet switch that's providing a lot of data. And all of this is integrated with our software called Gold VIP, integrated together to bring data to the cloud with visualization. So it's really exciting. It's been great to partner with AWS because bringing best of breed of both is important to bring this complete solution to market. So I will turn it back to Jeff. Hopefully, this demo will all work out. I think it'll be exciting to see some of this in action, and thank you for your time.
Perfect. Thank you, Brian. I think we've gotten our technical issues out of the way, maybe. All right. Ready? Wait for it. Look at that. There we go. We're already off to a good start. So this is the thing that you guys came here for, to actually look at the product itself. So what you'll see here, this looks like an AWS console, so hopefully this doesn't surprise anybody. But this is now live, so you can go and check this out today. It is in preview, as announced by Adam yesterday, so you can go and create these models. We do have a free trial as well, so everything that you see me do today, you can go and do. We have a couple of pretty easy to start processes, and a couple easy to start demos available for you as well, to create virtual vehicles in the cloud, of course, and then replicate those. We had a bunch of interns driving around last year, so we recorded all their data. All right. So the first thing I want to do in this demo is create a vehicle model. And this is the first thing that an automaker or a customer would do in this case as well. I first need to tell the service, what are the signals? What represents my vehicle? I would do this in the vehicle models right here. So you'll see here that I have a few vehicles that I've already created. A brand new customer, of course, wouldn't see anything. Why is it not showing? AV, we've got a frozen screen. I promise it's not me. Shouldn't have said anything about AV issues because I jinxed myself. At this point, I'm going to have you come and do the presentation. There we go. Yep. All right. The star of the show, ladies and gentlemen. All right, so this is the vehicle model area that I was talking about. This shows your different vehicles. A new customer, of course, wouldn't see anything here. I have a few that I've created, but let's create a new one. It really doesn't like my touch, I guess. All good. All right. I'm not going to say anything about it working now. So let's go ahead and create a vehicle model. Look at that, we can see it. So the first thing I need to do is name it. I'm going to create a name, which is reInvent Demo. Let's do 5. You can add a description here. This would be any of the description just to signify your vehicle. Now, this is the catalog, or as I like to call it, the supermarket of signals. So this is existing signals that I've already created based on my models. So if I'm creating a new vehicle model now, I first have to go, and I first can go and look and see what are the existing signals that exist at my company. So for instance, I've created a few here, and I've created this structure as well. All of this structure and all of these signals are configurable by the customer. But for instance, if I wanted to create a new vehicle, let's say that I want to take body. My vehicle has a body color. I want to define it by that. I want to define it by the number of doors, perhaps. And then one of the things that I'm interested in is tire pressures. So I'll take axle. This is kind of the nested structure here. I'll pull these. What I'm doing is I'm selecting signals and I'm selecting attributes that make up my vehicle model that I'm creating. You'll see on the side here we have a preview. So these are all the signals that you're selecting. This is all I'm going to do today. The next step is any new signals. So what this is if existing signals don't completely make up your vehicle, let's say you're creating a concept vehicle, or you have a new feature that has a sensor or a signal that didn't exist previously, this is where you'd create a new signal. What you would do is you would upload one of those standard files that we've talked about. So for instance, a CAN DBC. AWS IoT FleetWise imports that file and then is able to parse out the different sensors and signals that we see within that file. So for instance, that file contained throttle position, engine airflow, engine torque, etc. Each one of these has this amount of data that was parsed in, but it doesn't have data type. And the key here is that this is where you tell the service, and this is where you define how you want to consume that data. Irrespective of how it's sent over the vehicle bus itself, how do you want to consume that data? How do you want your systems and your users to consume that data? So for throttle position, for instance, we can make that float. The other piece here is path. This is where I create that hierarchy structure. So depending on where that sensor sits on my vehicle, I can organize it by domain. I can organize it however I want. To fit into my structure, it would be vehicle.powertrain. .engine. This is where I'm able to create and manage that hierarchy. If I don't want to add any of the other sensors, I don't have to add every signal that was parsed. So I would simply go here and select them all but this. Remove these. And what this is saying is I want to import one new signal to my catalog and one new signal to my model. And then I'd hit next. Right. The second part is adding attributes. So these are things that define my vehicle that aren't necessarily measured. So this could be things like number of doors, body color. Could be fuel type is another one, whether it's diesel, gasoline, et cetera. These are the things that define your vehicle that aren't necessarily measured. So if I want to add fuel type, I can do that. This would be a string. Similar to how I manage the path of the sensor itself, I would also manage the path of the attribute. Where do I want that to fit in my vehicle? Is it under body? Is it under chassis? I can define all that metadata about my vehicle within that same hierarchy. So for me, I would put this in vehicle, powertrain, engine, and then next. So the next part is that I'm going to review this model that I created. It's going to review the sensors from the signal catalog that I pulled. So I'm pulling body color, I'm pulling number of doors as my two attributes, and then I'm also pulling tire pressures for all 4 tires. You can see here that if I add descriptions, you'll also see those. Those are to give your engineers and your downstream consumers of this data better context into that signal itself. It's summarizing any signals that I've imported that I'm adding to the sensor, to this model. If I add a new model or a new sensor to that model or a new attribute to that model, it does automatically get added to the signal catalog, so I can use it in subsequent models or later on models that I create. I would then simply hit create. I am going to cancel this though because I've already created a bunch of vehicles. So the next step, let's take a vehicle that I've previously created. So let's call it reInvent Demo 4. This is what would be shown after you create a vehicle. And it's simply giving you a summary. We've created an ARN for you to use. The signal catalog is the same across your entire catalog or across your entire fleet, typically. The next piece is I've defined and I've controlled and input what makes up my vehicle. The next step is to tell the service how to read the actual data on the vehicle itself. We do this through something called a decoder manifest, which is right here. You can have multiple decoder manifests per model manifest. The reason for this is we anticipate automakers and customers to want to be able to manage variations within the decoder manifest. So for example, if I have one car model with and without heated seats, each one may have a different decoder manifest because even though just the option has changed, that vehicle network has also changed. You can manage that variability within the decoder manifest while still maintaining the same model. That allows your downstream data consumers to still have a consistent data schema. So in order to create a decoder manifest, I would create a decoder manifest right here. I would give it a name. 4. Enter a description. So the first thing I need to do is we mentioned that there's multiple networks on the vehicle itself. This is where you need to tell us where that signal lives on the vehicle network itself. So right now we support CAN and OBD. Soon we'll support more interfaces on the vehicle as well, such as Ethernet, as we know that's an important one. I'm going to interface, I'm going to make this CAN, and I'm going to call it CAN1. We give you a unique interface ID that you can use later on. You don't need to, we generate it for you, so you don't need to create it, but you can edit it if you wish. The second thing you need to do is tell us what sensors or what signals are on that network that you just defined. So I'm going to select all. And from here, I've imported now these sensors. It's giving you the path saying vehicle chassis Excel. It's giving me a friendly name, and I now need to tell the service what is that sensor or what is that signal called on the actual bus. We know that's not going to be a human readable signal on the actual network, so you need to tell me where to go and find it. That's typically defined in the same file that you use to create the sensor to begin with, which is that DBC file. So I take the same one and upload it. If we're able to match the two, if the name is common, is what we typically look for, common attributes, we'll try to match as much as we can. In this case, I've changed the left tire pressure, the right tire pressure to be more human readable. So we weren't able to match it. But what I would do is I would go in and start looking. Okay, here are the different sensors and signal information that we parsed from the decoder manifest. Which one matches to which? Which one maps to which? As an engineer as an engineer configuring this service, I would know what sensor my model manifest would map to my decoder manifest, because I'm the one theoretically that's been building this on my car. So for instance, I would say, I know left rear tire pressure is this guy, and right rear tire pressure is here. Left front, right front. What I've done here is I've mapped my model manifest, so my human readable, my friendly, my consolidated scheme. I've mapped that now to my individual vehicle. This is where mapping and managing that variability between the models actually comes to fruition. Here I'd hit next. I'm again given a summary, which basically says, here's the decoder manifest that you're creating, here's the data around it, here's the sensors and the signals that we've paired with the corresponding matching information. And then I'd hit create. So it's created. You can now see underneath this model that I have, reInvent Demo 4, that decoder manifest that we just created is right here. So the next step in this process, once I have this virtual vehicle design twin, so to speak, is to create the actual vehicle. This is done through a create vehicle CLI that we have as well. I've also created a couple of vehicles for us in the essence of time. So here you can see we have two vehicles in my made-up fleet, one called FW Demo 0 and one called FW Demo 1. These vehicles are created based on this decoder manifest and based on this model manifest. So it's telling me that this individual vehicle is represented by this model, and here's the decoding information for this individual vehicle. Once I have this, the next step in our process is to define the data that I actually want to collect. Now, we have two ways of collecting data or defining the data that you want to collect. One is time-based, one's event-based. These are simple JSON documents. Let's take a look at one of them. So this one's a time-based, or as we call it, heartbeat. This is the vital statistics of a vehicle. So in our example, this is saying, I want to collect engine speed, ambient air temperature, engine coolant temperature, et cetera. I want to collect that every 10,000 milliseconds, or every 10 seconds. This is what we're calling a time-based campaign. Relatively simple. You can make these as long or as short as you wish. The next type of campaign would be event-based. And this is collecting certain information when something of interest happens. So in our case, or in our example, I want to collect engine torque and brake pedal pressure when brake pedal pressure is greater than 7,000, in this case, 7,000 kilopascals. The key thing here that's interesting about event-based is I can control pre and post-event. So I can define if I want to collect sensors before an event of interest happens or after. So for instance, in our example, I'm saying I want to collect these two signals for 1,000 milliseconds after you detect an event. The same can be said about pre. So if I want to know something that's happened prior to an event, AWS IoT FleetWise gives you that ability. It says, I want to know the leading 3 seconds until this event was detected, and then send it to the cloud. You can do both pre and post in the same event. So the next step, once I've defined these and I've built out the data that I want to collect, I know now what I want to collect, the next step is to actually send it to the vehicle. We do this through a service called Create Campaign. And this is a command that we have in the AWS CLI. You can see here that it's a relatively simple call. I'm basically just naming it. So let's name my campaign name time-based demo 5. I'm taking a signal catalog ARN. So the signal catalog is basically that supermarket of signals that we create. That's created for you, so that stays relatively constant. Target ARN is the vehicle that you want to deploy this campaign to. This could be one vehicle, or it could be a fleet of vehicles. It could be a grouping of vehicles, but each one would have its own ARN. The campaign itself, this is the JSON file. So this is what the instructions that I have. So for instance, for us, it's going to be this guy, this campaign OBD. I'm defining where that is, so it could be a local file, et cetera. And I would send this in my shell script. Perfect. So what this has done now is it's created time-based demo 5 campaign. So that's created a campaign for us now. So the only difference here, though, is that I haven't actually sent it to the vehicle. And this is a safety measure that we actually built into AWS IoT FleetWise. This is in case you accidentally send a campaign to 1 million vehicles. You don't want to do that, since that incurs cost. So the state that this campaign is in is it's in a running state, or it's in an idle state. And what that means is that it's created, but it hasn't been actually approved or sent to the vehicle. So in order to do that, we have to approve the campaign. This theoretically would be either a manager at the company or somebody that has the authority to go and say, yep, I'm willing to incur that cost to go in and send this new campaign to these vehicles. In order to do that, I approve the campaign. This is a relatively simple command as well. The only thing I have to change here is the name of the campaign. So time-based demo 5. All right, and what you see here is now the status has changed to running. What that means is that this campaign is actively being deployed to these vehicles. Right now, it's a fleet of 1, so this is a relatively simple operation. But when it happens to a fleet of, let's say, 1 million vehicles, this becomes more complex. So as these are deployed to vehicles, we know that vehicles are inherently not connected. So imagine parking in a parking garage underground. That vehicle is no longer going to be connected to the internet until it comes back out. With AWS IoT FleetWise, we manage the deployment of these campaigns for you. That's one of the key benefits as well. We are able to retry when that vehicle is underground. We're able to detect when it comes back to connected, when it comes back connected to the internet, and then deploy this. You as a user have the ability to check this through a simple operation called getVehicleStatus. When I look at this, so all this is doing is it's saying, hey, what campaigns do I have on a given vehicle? In this case, FW Demo 1 is the vehicle that I'm deploying these to. So this comes back and it returns all of the campaigns that are active on that vehicle. So you can see here I've created a bunch of vehicles over the past few days. Healthy means that the vehicle has downloaded the campaign and it is actively running on the vehicle. We are collecting data. The vehicle is collecting data per that policy that you sent to it. Running, or created on the other hand, means the vehicle's aware and I've downloaded, but I haven't enacted it necessarily because you didn't tell me to. So that is another kind of state that we have on the vehicle. You can see here that time-based demo 5, the campaign that we just created, was deployed to my vehicle and it is in the healthy state. So what that means is that that vehicle is now receiving, or it is collecting data and sending it back to the cloud. What that looks like is in TimeStream. So if I go back to TimeStream and I run a quick query, we will see data coming in from that vehicle that we just created, right here. And what we can see here is this event ID. Right now, because we did a time-based, that event ID just represents a point in time, essentially. However, when you have event-based collection, that event ID will be a trigger event. This will say, hey, this event happened. All of these sensors and signals are associated with this event. All right. So that concludes our demo for today. Let's see if I can do this correctly. I cannot. Can we go back? Presentation, please. Maybe? Nope, not going to. Okay, that's fine though. So essentially, Brian and I are up here willing to answer some questions for you. Just come up to the front of the stage. But thank you again for joining us today. It's early days for this service as it's less than 24 hours old. But thank you again for joining us, and we're excited to work with you and work with automakers and customers on this. Thank you again.